Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss realizing logic gates by using transistors. Let's begin. First, OR gate, which is also known as the inverter. Inverter in the sense, if we prefer the truth table, A as input, Y as output, that is A naught, that bar symbol or prime, read as A prime or A bar. The possible inputs 0 and 1. In output, for low input we have high output 1, for high input we have low output. That is the truth table of NOT gate. As the output is just reverse of that of input, that's why we call it as inverter. And we symbolize it a triangle and a circle. The input A, we have output Y is equal to A bar. Now, we realize that NOT gate by using transistors. Let me consider an NPN transistor . NPN transistor and it is in the common emitter mode. Let me select it as common emitter mode. The emitter of the transistor is common. So it is connected . To a resistor . Negative V . It is grounded . Here VCC, load register RL, as the output. So the output and the output. Here is the input. Input A, output as Y. Let me understand the action. When A is equal to 0, input is equal to 0, let that input section we have a square wave signal is applied to that of input. Square wave signal that signal is a square wave signal. That portion is 0, that portion is 1. When there is no signal or that input port is connected to ground, we assign as A is equal to 0, input as 0. Then the base of the transistor becomes negative at that of situation. The negative potential drives the transistor to cut off condition. Hence, no current flows through that of collector circuit. The supply voltage plus VCC, common collector, is obtained at that of output section. In other words, we can say the output reaches high. Here the input is low, but we obtain the output as high, and in binary system we represent it by the binary bit 1. When A is equal to 0, at output we have 1. In this way we explain the case as A is equal to 0, then output Y is equal to 1. So the output symbol one 0. First case, as A is equal to 0, A is equal to 0 means no signal, or we can say the input port is connected to that of ground. That's why we assign A is equal to 0. Therefore, the base of the transistor becomes negative. since the base of that of transistor become negative, as a result that negative potential, the negative potential drives the transistor to cutoff condition, therefore no current flows through that of collector. That is the collector circuit. In that of collector circuit there will be no such of current flow, and the supply voltage plus VCC is obtained at that of output. The supply voltage plus VCC is obtained at the output. Means it is high or 1. Therefore, when A is equal to 0, then Y is equal to 1. Next, case number 2. When A is equal to 1, then what happened? When sufficiently large positive voltage or positive going that of square wave is applied in input section. Here we assign A is equal to 1. We apply when sufficiently large positive voltage or a positive going square wave is applied in the input. As we say A is equal to 1 in that of binary notation. Therefore, the base of the transistor becomes positive at that of situation. Base of the transistor becomes positive, and the base emitter junction is forward biased. Therefore, the transistor just behave as a closed switch. That's why transistor behaves like a closed switch and conducts current in the collector circuit. Therefore, the collector potential drops to low, or we say it as 0, and that shown in that of output, that shown in that output. Therefore, when a is equal to 1, so y will be 0, and when a is equal to 0, y is equal to 1. In this way we realize the NOT gate, which is basically known as the inverter, by taking transistor into consideration. Two cases are discussed. Next, OR gate. The operation of OR gate we can realize by taking transistor into consideration. For OR gate, we know the symbol of OR gate as two input A, B, as output y is equal to A plus B, that is A or B. In truth table, input A, B, output as A plus B, possible inputs 0 0, 0 1, 1 0 and 1 1 in output. For that of OR condition, when two inputs are low, then the output is low, otherwise it will be high, 1 in all conditions. And the truth table for OR gate. Let we realize that OR gate situations by taking transistor into consideration. Therefore, we use NPN transistor, and these two transistors are joined parallel. For that of OR gate, and the output we have high. If either any one of that of transistor is conducting, as we show in that of logic section, either any one of the transistor is 1 or high, then we have the output as 1. So output so high, either any one of that of transistor is conducting, and the output will be 0 when each transistor is not conducting. There will be no such flow of current through that of two transistors. Let me explain all the possible situations one by one. First condition, case number 1. Case number 1, when A is equal to 0 and B is equal to 0, the two transistors input are 0. At that of situation, what happened? The emitter of the transistors are connected to that of ground through that of resistor Re, which the output is taken across that of resistor. Both the low inputs are 0 0. Turn that of transistor into cut-off conditions. They are switched to off position. Therefore, these two transistors just act like the switched as open switched, that is the open switch situation. Therefore, for case number 1, we clearly known it is just like this, plus VCC that is the output Y, and these two transistors, when the input A is equal to 0, B is equal to 0, it is act like a switch, that is a open switch. Here is the open switch. Therefore, at the output we always have 0. So first situation, when 0 0, we have 0 condition. Next, case number 2. Case number 2, when A is equal to 0, B is equal to 1. Then what happened? Same situation, A is equal to 0, B is equal to 1. So A as open and B is short circuited. So in figure it is clear. Potential VCC, here is the output. Since A is equal to 0, so first transistor T1, just like the switch as open switch, and that section is behave like the short circuited. And the circuit is completed. So in output we have 1. So 0 1 result as 1 in that of output section. Case number 3, just its opposite, as A is equal to 1, B is equal to 0. Same situation, when A is equal to 1, so transistor 1 as short circuited and transistor 2 is just like open switch, and due to that of transistor 1, the circuit is the circuit is completed, and at that of output section we have high or 1 in figure. So just like this. Y as output, A is equal to 1, so that portion is short circuited. B is equal to 0, the transistor just like open switch, plus VCC, and the circuit just completed, and at output section we have high output 1, that is 1 0 situation we have 1. Next, last situation, 1 1 condition. Case number 4, when A is equal to 1 and B is equal to 1 situation. Same thing, these two transistors are short circuited and overall circuit is completed, and at output section we have 1. Resistor is grounded. Here at output Y, that is the output. in input section plus VCC. Therefore, in that of A also short circuited, both are short circuited, both transistors short circuited, the total circuit is completed, and at output section we have one output. In this way we realize OR gate by taking two transistors are parallel connected with each other. All four possible situations for OR gate are understood by using the transistors. Next logic gate, AND gate. We explain AND gate by using the transistors. We realize AND gate by using transistors. For AND gate, when the inputs are A and B and output Y is equal to A dot B, A and B. In truth table, A, B, output Y is equal to A dot B. Possible inputs 0 0, 0 1, 1 0, 1 1. In case of AND, when two inputs are high, at output we have high, otherwise it will be 0. That is the truth table for AND gate. These cases can be easily understood by taking transistor. So we have two transistors T1 and T2. These two transistors are connected with each other in series to show AND gate, and the transistors are just like that of a switch. So when we have the possible situations as 0 0, so first transistor and second transistors are the inputs are 0. Since the both inputs are 0, these two transistors just as open circuits. Therefore, all the connections are removed from that of plus VCC and that of output section. Therefore, 0 current through that of resistor RE we obtain. So these two just like that of a switch off condition, and at output we have off. So it is clearly shown that case number 1 as A is equal to 0 and B is equal to 0 situation, what we have? That is the resistor RE. Here is the output. Output Y plus VCC. Transistor 1 is open, transistor 2 is open. Finally, at output we have low signal, that is 0. Same thing, case number 2 as A is equal to 0 and B is equal to 1. A is equal to 0 means transistor 1 as open and B as closed. Therefore, at output we have 0. figure it is clearly shown. Open, that section is closed, and output that is open, that one is closed, and for plus VCC. Therefore, at output we have 0. That section is not connected to that of closed part. Therefore, that VCC value is not found out through that of output. Therefore, we have low result or 0 in that of output. Case number 3, just it opposite. When A is equal to 1, B is equal to 0. A is equal to 1, that is closed, B is equal to 0, transistor 2 is open. Closed, next as open, it is connected to that of ground, and the output Y, as we have output plus VCC. A is equal to 1, so it is closed, B is equal to 0, it is open, and again that is open, so VCC is not completed, so at output we have also 0. Case number 4, when A is equal to 1 and B is equal to 1, means transistor 1 and transistor 2 both are closed, it is closed, again it is closed. Therefore, at output Y we have 1, that is closed, this one is closed, 1 1. So, VCC just connected to these two transistors. Therefore, the entire circuit is completed, and finally at output we have high or 1. So, that truth table possible situations are understood by taking two transistors connected in series. For that of AND gate can be easily understood. So, with the help of this video lecture, we understand the realizing logic gates using transistors. NOT gate, which is called as inverter, we realize the situations for NOT gate by taking transistors, case number 1 and case number 2. Next logic gate, OR gate, its possible situations are understood by taking transistors, all these cases. Next, for AND gate, all situations are again understood by taking transistors in consideration. So, with this useful and informative notes, let me wind up this session. Thank you.